Okay, now once we know how to do rebalance, let us now go back to search. Search is nice because search doesn't modify the tree at all. So search is as usual. Search for v in the nil tree is false. Search for v in node whatever TL xtr is, you compare v and x. If v is less than x, then you search in the left subtree, and if v is greater than x, you search in the right subtree. If v and x are equal, you return true. Okay, so this is good. Let us look at insert. Insert v into nil will just give me node nil v nil, but I have to give the height also as part of the node, so height is 1. Inserting v into a tree T which has the pattern node h TL xtr. Okay, now we have to calculate. Let notice here once again, so I've written NTL and NTR. NTL is the new tree on the left and NTR is the new tree on the right. NTL means insert AVL, insert V into the left tree. NTR is inserting V into the right tree. Notice that both will not be necessary, only one of them will be necessary. But Haskell is lazy, so only that recursive call that is necessary, that is used, will be invoked. That is necessary will be invoked. Okay, good. So this just makes it easy to program. NHL is the new height of the left subtree, and that is nothing but 1 plus max of height of the new tree on the left and height TR. NHL is new height of the overall tree in case insert happens in the left subtree. Similarly for NHR. Okay, great. Okay, so NHL is what? 1 plus maximum of height of NTL and height of TR, right? And NHR is 1 plus maximum of height TL and height NTR. So this is the case when the insert is happening in the right subtree. This is the case where the insert is happening in the left subtree. Okay, fine. So these are all my local definitions. And what do? Compare V and X. If V is less than X, then you just say node NHL NTL XTR. So you insert in the left subtree and you rebalance, right? Because after inserting your there might be an imbalance only at the root node, because you will recursively keep on rebalancing, because this NTL will involve a call to insert AVL of VTL. That insert call will have done a rebalance. So at the root level of NTL, NTL is all balanced, but after you modify the left subtree and you try to put together NTL and TR, there might be an imbalance there. So you have to just do a rebalance here. Similarly, if V is greater than X, you insert the node in TR, you just take TL as the left subtree, but at this level there might be an imbalance, so you have to rebalance. If V is equal to X, you don't have to do anything, you just return T. Okay, so this is the entire code, and now the number of rebalances required is you're just making a recursive call, and after coming back you're doing a rebalancing here. In the course of the recursive calls, you would have made rebalances, but you will only make rebalances at each node that you visit. So therefore, there are only log n many rebalances that you do, really, right? Because originally you had there are only height of the tree many rebalances that you do, and the height of the tree is always bounded by log n, 2 log n or whatever. Okay. So now insert, we have delete max is just the same as usual, except that we need to readjust the heights every time. So delete max of node TL x nil is x comma TL. X is the maximum element and TL is the residual tree after you removed x. Delete max of node h TL xtr is y, and rebalance. Yes, even here you have to rebalance, because once you because you deleted something and heights might have changed and you have to rebalance. So, rebalance of node NH TL x Ty, where y comma Ty is delete max of Tr, and instead of Tr you keep Ty, but if you try to put together TL and Ty you might have a problem. So, you will have to rebalance. NH is the new height. Earlier you had 1 plus max of height TL and height TR, which was stored at that node. Now you will store 1 plus max of height TL and height TY. Okay, this is all the things that you need to do, and you just need to do a rebalance here. And similarly, because this recursive calls of TY is a result of the recursive call to delete recursive call of delete max. So at that point you would have done a rebalance, but in any case the rebalance will only happen along nodes of a path that this procedure visits, and that is proportional to height of the tree, which is bounded by some constant times log n. Okay, so this is done. Once delete max is done, you have to do the overall delete AVL. So, okay, so what you do is deleting the element v from the nil tree will just result in nil. Deleting v from t, where t is of the form x TL TR. Let's just look at the main code. Compare v and x. If v is less than x, you have to delete v from the left subtree. If v is greater than x, you have to delete v from the right subtree, right? And deleting v from the left subtree means that you will replace the left subtree, which was earlier TL, by NTL, where NTL is given by this. Delete AVL of VTL. NTR is given by this, delete AVL VTR, and once again Haskell is lazy, so it is not that it will go and eagerly compute these things, it will compute only whichever call is necessary, okay, whichever call is actually being made, only then it will compute. And each time you do this, you can readjust the height as well, NHY, NHL, NHR, so you can do all this, and fine. So, even here I am saying delete max of TL, but delete max of TL might not be needed. If it is not needed, it will not be executed, okay. But the point is, if v is equal to x, then if TL is empty, you just keep it to be TR, else you do node NHY TY Y TR, which is the delete max this thing, and at every stage you have to, if you have replaced something, you have to rebalance. So, in this case you have to rebalance. But the rebalance is only along a path in the tree, so which is proportional to the height of the tree. Okay, great. So that is basically it about deleting a node from a particular value from an AVL tree. Right. So let's look at the complexity. Left and right rotates take constant time. Rebalance takes constant time also when both subtrees are balanced. Okay. So, search takes time proportional to the height of the tree. Insert and delete spend constant time on each node of some maximal path and potentially maximal path, and that is proportional to the height of the tree, but height is bounded by log n, right. So, this is the whole point. So, each operation takes order log n time. So, a sequence of n operations So, if you imagine, if I keep inserting one element after another into the AVL tree, start with an empty AVL tree and I keep on inserting one element after another, so I can crudely say that, let's say I insert 100 elements, I will crudely say that the even though the tree height might not be this at all times, I will say that the tree height, the maximum tree height I will ever reach will be 2 times log 100 plus 1. To log 100 is log to the base 100, which is 7, 2 times that is 14 plus 1 is 15. So, my tree height will never go more than 15, and so I will have like 100 into 15, which is 1500 steps I will perform to do 100 insertions. But this is also the same case with deletions. If I do 1000 operations where arbitrarily I do insert, delete, etc., and it is the case that never ever the if there are 1000 operations, And typically with these kind of operations, you will have that search will be the most often performed operation, then will be insert and then will be delete. Let's assume that there are like 600 searches, 300 inserts and 100 deletes. Okay, your size is always less than or equal to 300. So height log 300 is less than or equal to log 512, which is 9, right? So 2 into 80, 2 into 9 plus 1, right? So your operations do not, so overall all 1000 operations put together take some fixed constant times 1900 steps, 19,000, right? So this is the kind of estimates you can make. Okay. So a sequence of n operations takes at most order n log n time. Now you can have other useful functions. The empty AVL tree is just nil. You can check if an AVL tree is empty or not. Is empty of nil is true, is empty of anything else is false. You can create an AVL tree and that is nothing, you can just do a fold R of insert AVL, empty AVL. Start with the empty AVL and keep on doing insert AVL of every element, and each insert takes time log n. There are overall n elements that you do. So to create an AVL tree you require time n log n. And you have this in order, okay, which you recall, if you recall, in order is this thing, the same go, I have written it in a different notation. In order of t is t plus colon empty list, where nil plus colon xs is xs, node whatever tl xtr plus colon xs is tl plus colon x followed by tr plus colon xs. Okay, so you have xs, you so you flatten out tr here, then you put x after that, and then you flatten tl before this. Okay, so everything in tl comes here, x comes later, and then tr comes later. Okay, so this is just in order, and this takes order n time. N is the size of the tree. Right, so you can sort a list in order n log n time actually by doing this tree sort. Recall earlier that we showed a tree sort which is actually in order dot from list, same thing. You can do an in order or create AVL. The difference is that earlier in that tree sort we couldn't have given any time bound, but now we can give a time bound. Create AVL takes time order n log n, this takes time order n. So overall this tree sort takes time order n log n. Okay, great. So this is a very nice side effect of having your AVL trees. You can have other useful functions. Recall that create AVL L, yeah, so you do in order of create AVL L, that sorts the list L, fine. What if we want a size balanced tree T such that in order of T is equal to L? Okay, this is not about sorting, not about sorting. Start with any L, find a tree, find a size balanced. I will tell you why this is useful in a minute. This is something that we have seen multiple times before. This is actually if L itself is already sorted, then T will be a search tree, otherwise it will not be a search tree. This is just a smart create tree that we saw in a previous class, and if you want to recall, it is this. Okay, we will call it in order tree. this works in order n time, that much is clear, but what I need to do is first of, so this go once again will take an integer and a list, and it will try to create a tree with the first k elements of that list and return the rest of the list as a, return the remaining elements as a list, okay. So that is this pair. So if I make a tree with the length L elements of the list, then the remaining elements is the empty list which I can discard. So that is why I am here doing first of go length L of L, and then I am taking the first, discard the second part which will be the empty list. So go 0, if I want to create a tree using 0 elements of access, it is just nil, and I have not consumed any elements of access, so I will just return this. If I want to create a tree with the first n elements of access, then it is this tree followed by z's, which is the remaining elements. But how do I calculate this? What I do is, instead of taking n elements in one go, I will take first m elements, which where m is n div 2, and create a tree TL. Then I will have some remaining elements, call this y colon y's, pick out y and make it the root here, and then I have y's, which is all elements after the first m elements, first m plus 1 elements. Now in this, if I pick n minus m minus 1 elements, that is what will add up to n elements, which I wanted to do originally. So I do go n minus m minus 1 elements, then that will leave over some elements which I call z's. This will clearly be drop n of x's, and this will be this tr will be the tree that I create from these elements. So there are just two recursive calls, go m x's and go n minus m minus 1 x's, and here the time complexity only depends on the number n minus m minus 1 or m or whatever. It does not depend on the list, on how large the list is. So you will actually see that T of n is T of m plus T of n minus m minus 1 plus some constant, but this is like T of n by 2. So you have 2 T n by 2 plus some constant, and this is actually order n. Okay, okay, fine. Okay, fine. So I have this in-order tree. The important part is that this is actually size balanced. Where will I use it? I will show you where you will use it. Now you can actually save this module in avl.hs. AVL, empty AVL, is empty, all these functions you can provide, and then you have all these definitions about AVL, show, whatever utilities you want to define. And you can use this to define a set ADT, which, remember, we started out with the set ADT. Originally we implemented the set as a list, and then that was not very effective or efficient, because to perform n operations you would require order n squared time. How do you do this set? For set I want to create, this is the type constructor. So value, so is of type set A, this is of type list A to set A, and then I can do insert into, delete from, search, standard. But given two sets, I can take the union, I can do the intersection, and I can take the difference of one set from the other, and this is where that in-order tree will come into play, as you will see. So how do I show a set? I just do set is stored as a tree, but I do not need to reveal it. I will just do in-order traversal of the tree, that will make it sorted order, and I will show that sorted list. Okay, this is my show. Empty set is just set, the wrapper applied on top of empty AVL. Create set is just you create an AVL tree and then you put the wrapper set on top of it. Search for x in a set T is nothing but search AVL for x in T. Inserting x into a set T is nothing but the set wrapper provided around insert AVL of x into t. Delete from is similar. Delete from of x from set t is nothing but the set wrapper put around delete AVL of xt. Okay. Now comes union. Set union is nothing but if I have to do set t1 and set t2 and if I want to do union, I put the set wrapper around in-order tree. I form the in-order tree of union merge of in-order t1 and in-order t2. So, if I have two trees, I do in order. So, this will be a sorted list, that will be a sorted list. I know already that I can do merge for two lists and create one. If I have two sorted lists, I can create one sorted list out of it. Except now I want to do union, which means that I want to discard duplicate elements. So, I have this union merge where union merge of empty list y's is y's, union merge of x's empty list is x's, union merge of x colon x's and y colon y's. If x is less than y, it is x followed by union merge of whatever. Y is less than x, then it is y followed by union merge of these things. But if x is equal to y, I retain only one copy, x followed by union merge of x's y's. Okay, I gobble up this element in both lists, and this is assuming without duplicates. Is a sorted list without duplicates, elements of this, I mean, which represents the union, represents x's union y's. Okay, great. And if I can do union, I can also do intersection, because all I need to do is just do intersect merge, where intersect merge says that if x is less than y, then I know for a fact that x will not be in the intersection. So, I just do intersect merge x's y colon y's. Y is less than x, I know for a fact that y will not be there. So, I do intersect merge of x colon x's y's. If x is equal to y, I retain one copy and then just proceed as usual. And this in order tree will give me back a size balanced binary search tree, because once I do intersect merge, I will, this whole thing is sorted. If I apply in order tree on a sorted list, I will get a size balanced binary search tree. And size balanced is also height balanced, so it is indeed an AVL tree. So, that is all I need to worry about. Diff merge is similar, so that this will find set difference. Okay. So, this does it. So, all I need to do is to show you code and see how actually, and show you how actually AVL tree works. I will do that in a minute. But just to summarize, AVL tree is a fundamental and non-trivial data structure. It allows us to efficiently implement the set ADT. You do search, insert into, delete from in order log n time. You can do union, intersection and difference in order m plus n time, because you have a tree representation of a set. You can do in order n time, you can do in order of that in order m time, and you can do union merge in order m plus n time, and then you can create an in order tree from that in linear time again. So, it is overall order m plus n time. It is an illustration of the power of Haskell, because mathematical definitions are almost directly transcribed into code, especially things like rotates. And the power of pattern matching is very evident here, because the complex rotates, you just had to express some pattern here and another pattern there. Okay, so this concludes the slides. I shall show you some I will run some code and show you how things work, and that will close the lecture. Let me go to VS Code now. So, you can see that I have programmed all these things. I have a module AVL which exports AVL, empty AVL, is empty, insert AVL, delete AVL, search AVL, create AVL, in order tree, etc. And I have empty AVL, is empty, these are all things that we saw already, slope, rotate right, rotate left, rebalance. Okay, all of these things we saw. Insert AVL also we saw, right? All these things we saw. Create AVL is just this. In order is just this smart in order which works on order n time, and this in order tree is also the smart thing which works on order n time. The rest of the things are about displaying a tree, but the point is now I have to show you what happens if if you insert into this thing. So let's I have another file here called v11. Yeah, here I am actually able to use AVL. I have this rand ints etc. installed here, and I also have a rand AVL method. So I will first show you this rand ints. Let us take 20 elements. Each element is between minus 50 and plus 49, let us say. Okay, so I have this. Let us see what excess is. It is this thing 43 minus 36, whatever. Okay, so let's try to actually do it step by step to show you how things happen. Insert AVL 43 empty AVL. Okay, I get something which is just 43, just the node 43. Suppose I insert AVL minus 36 into it. Minus 36. Okay, 43 minus 36 is less than that, so it goes to the left. 32 is next. Okay, now you see already that so 32 is to the left of minus 36 and it should go to the right of minus 36, right? So it will be 43 and then minus 36 is already there to its left. You will try to search from 43, you will go left, from minus 36 you will go right. But now you have a situation where the left subtree has height 2 and the right subtree has height 0. Furthermore, the left subtree has slope minus 1. So you will do the appropriate thing, the appropriate rotates, and now you see that you again have a binary search tree, because 32 is at the root, minus 36 is to its left, 43 is to its right, but it is balanced. Okay, this is the important point. The next thing I want to do is insert 45 into this. It should go to the right of 43 and it should be fine, because there are height balance is still maintained. Height difference of at most 1 is okay at every level, that is maintained. Now you have minus 22. This might create a problem or it might not. Let's see. Minus 22 should go to the right of minus 36 and it will once again create a problem and trigger some rotates. Okay, so you see that it has no, it has not triggered any rotates. Minus 22 goes to the right of minus 36 and it's all fine, everything is fine. You still have height balance maintained. Let's see what the next element is. Minus 36. Minus 36 is a repeat, so it shouldn't modify the tree at all. Right, it doesn't modify the tree at all because it goes there and sees that minus 36 already exists, so it doesn't do anything. Minus 23 is next. Let's try to figure out what might happen. Minus 23 should go to the left of minus 22, but to the right of minus 36. Now that will create an imbalance because your left subtree has height left subtree rooted at, considering the tree rooted at minus 36, its left subtree will have height 0, right subtree will have height 2. So you have to do a left rotate. Let's see how exactly the left rotate is done if this happens. Okay, yeah, some complex left rotate. You first do a right rotate of the right subtree and then do a left rotate, which is why you have this situation. minus 23 has actually become the root of the left subtree, right? But at every point there are some complex changes that are happening, okay? You are in a binary search tree as we did earlier, if you did an insert, everything will go to the leaf level only at every point of time. Here that's not what is happening, but no matter what it is, the binary search tree property is still preserved and height balance is preserved, okay? And let's just complete this whole example. We had minus 23, minus 26, let's try. Okay, once again, you see, okay, there is no change at the top, minus 26 goes to the right of minus 36, which is fine, everything is fine. But if I try something very skewed next, it will create a problem. After minus 26, it is minus 48. So let's try that. That should go to the left of minus 36 and still there shouldn't be a problem. Okay, height balance is maintained. It's fine. Even though the size is larger, you see the size of the left subtree is much larger, but that's fine. Height balance is maintained throughout. That's all you care about. After minus 48, it is plus 27. Plus 27 should come to the left of 43. No, plus 27 should come to the left of 32 and to the right of minus 22. So, shouldn't be a problem still. What was the number? Plus 27. Okay, good. So, there is a lot of space to fill in without increasing the height. So, as long as it's possible, it will keep on maintaining this height. Okay. 46 is next, and 46 should come to the right of 45, and then that will trigger a rotate. Let us see how. 46 might end up, 45 will end up being the root, I think. So, let's see. Yeah, okay, 45 has become the root here. 43 has been pushed down to its left and 46 is at the rightmost, and things are still fine, okay. After that, it is 20, 24 minus 49. Let's try to remember. Okay, now there is some changes, because 20 should come to the left of 32, should come to the right of minus 23, and should come to the right of minus 22, should come to the left of 27, but then that will create a height balance. So 20 itself becomes, so you do a right rotate of the right subtree and then a left rotate. So that is why 20 has come here to occupy the place that minus 22 was earlier occupying, and to its left is minus 22 and to its right is 27. Okay, 20, and then if I recall right, we said 24 and minus 49, minus 29. So let's do 24. 24 should come to the left of 27 and it shouldn't be a problem. No, it will be a problem, because once 24 comes to the left of 27, if you look at the tree rooted at 23, its height will be 1, 2, 3, 4. But if you look at the tree rooted at 45, its height will be 2, and that is a difference of 2. So some wholesale changes have to happen now. And in fact, your root itself will change. 32 will no longer be the root. Okay, so let's see. Yes, indeed, 32 is no longer the root, 20 has become the root, because you have to left rotate and right rotate or whatever. Because of all these things, 20, you have to left rotate the left subtree and right rotate the overall tree. That's what has made this happen. Now minus 49 should go to the left of minus 48 and shouldn't be a problem. No, it is a problem, because you have to because it's a problem, because right now if you look at the tree rooted at minus 36, its height is 2, and if you look at the tree rooted at minus 22, its height is 1. But if you increase this, then this height becomes 2 and that height becomes this height becomes 3 and that height becomes 1, and that's a difference of 2. So you have to do some wholesale, you have to do some modifications for the tree rooted at minus 23, which is why now minus 23 has gone to the right side, minus 36 has occupied the place of minus 23. Okay, now there is a minus 29. Yeah, and it goes on and on. This time it didn't create a problem. Minus 29 is not a problem. Then we have 0, 17, minus 6, 27, minus 14. Wow. Okay, 0 has been added and some more changes have happened. 17 minus 6, 27 minus 14. Okay, so after all this, you have this kind of tree which is reasonably balanced, and you can see that there are around 20 elements, but the height is 1, 2, 3, 4, 5. Okay, so that's good enough. Rather than having 20 or whatever, you have a height which is balanced and which is limited like this. In fact, so you can actually try create whatever we called it rand AVL. I can call tree is rand AVL, and I have to give some parameters. I can say 30, elements with values between minus 100 and 99. I am creating a random AVL tree out of these. Let's see how tree is. Okay, so you have this. Okay, okay. So you can also play around with delete, and because of this show method, you can actually see how what exactly is the difference that happens. Okay, so this brings the discussion on AVL trees to a conclusion. In the next lecture, we will look at another data structure which is very useful. But for now, this is it. Thank you.